Welcome to StemTalk.
StemTalk. StemTalk.
StemTalk.
StemTalk.
Welcome to StemTalk, where we introduce you to fascinating people who passionately inhabit the scientific and technical frontiers of our society. Hey, welcome to StemTalk. I'm your host, Dawn Kornegas, and joining me today is IHMC's director, Dr. Ken Ford.
Thank you, Dawn. Good to be here with you.
Today we have a special treat. We're interviewing Dr. Mike Gernhardt, who is a NASA astronaut and researcher.
As we will hear during this interview, Mike Gernhardt's impact on NASA and space exploration, however, goes far beyond his direct experience in space. He's really helped shape the program in many ways. Mike was another easy selection of the Double Secret Selection Committee.
I can imagine. But before we get to today's interview, we have some housekeeping to take care of. First, we really appreciate all of you who have subscribed to StemTalk, and we especially appreciate all of the wonderful 5-star reviews piling up on iTunes. These 5-star reviews really help make StemTalk more visible on iTunes.
As always, the Double Secret Selection Committee has been continually and carefully reviewing the iTunes reviews with an eye toward selecting the best reviews to read on StemTalk. There are, as always, extra points for pithiness, wit, and, of course, lavish praise.
If you hear your review read on StemTalk, just contact us at stemtalk@ihmc.us to claim your official StemTalk shirt.
The shirts are flying off the shelf.
Today, our winning 5-star review was posted by someone operating under the moniker Paula Olivet. As soon as we hear from Paula Olivet, a StemTalk t-shirt will be on the way. Here's the winning 5-star review, which is titled, "I Wish This Podcast Aired Every Day."
This show takes science as a personal, academic, and professional venture, which it entirely is. It's not all pipettes and mice. It's ambition and unquenchable thirst for answers. Even when I think the episode subject matter is not for me, I still find myself completely enthralled.
Well, thank you, Paula Olivet, and the thousands of other StemTalk listeners who have helped make StemTalk a great success right out of the gate. Okay, now on to today's interview with Mike Gernhardt.
Fasten your seatbelts and check your oxygen levels as we head into space and undersea with Mike Gernhardt.
Mike Gernhardt received a bachelor's degree in physics from Vanderbilt University and a master's degree and a Ph.D. in bioengineering from the University of Pennsylvania. From 1977 to 1984, Dr. Gernhardt worked as a professional deep-sea diver and an engineer on projects around the world. He also served as manager and then vice president of special projects for Oceaneering International. He then founded Oceaneering Space Systems, which is a company that was formed to transfer subsea technology and operational experience to the International Space Station program.
Mike was selected by NASA for the astronaut program in March 1992 and is a veteran of 4 space flights, including 4 spacewalks. And as I mentioned earlier, his impact on the agency and how we do human spaceflight is really extensive.
In short, he brings his previous undersea experience to human spaceflight, where it continues to be directly and critically applicable.
Dr. Gernhardt's honors are many, but among them they include the NASA Distinguished Service Medal, which is NASA's highest commendation. As I said, he has a whole shoebox of other awards, which we will not recount here.
Absolutely. And joining us today for our interview with Dr. Gernhardt is IHMC colleague and former NASA astronaut Tom Jones.
StemTalk.
StemTalk.
So I'd like to welcome to today's podcast Dr. Mike Gernhardt.
Good afternoon. Hope everybody's having a great day.
Yeah, and we also have as our co-host Tom Jones.
Glad to be with you, Dawn, and with my good friend, Mike.
And I'm very lucky to be sitting here with 2 astronauts today. So, Mike, just kind of going back to your beginnings. So before you became an astronaut and a researcher, you were a scuba diver, and that was an extensive part of your career. How did you first get into diving in the first place?
Well, that's a long story, and I'll try to make it short. But as a 4 or 5-year-old, I was going fishing with my dad down in Florida, and I loved the fishing, but I was always interested in what was under the water. And so at a very young age, I think I was 9 or 10, on a family vacation, there was a guy that was doing scuba diving, and I was a competitive swimmer and so forth. So he taught me to scuba dive just enough to know that I loved it, and I saw the reef and all the fish and all that stuff. So it really inspired me. And then I came back to Ohio and got certified when I was 12, which is the youngest age you could. And then, did all kinds of diving, became a diving instructor when I was 18, and then worked my first couple summers in college as a scuba diving instructor and boat captain in St. Thomas in the Virgin Islands. And then I kind of had done everything you could do with scuba, and I was really more interested in the deeper, more complex diving. And so I got into commercial diving, first working as a tender in the summer in the Gulf of Mexico, doing deep saturation, helium-oxygen diving and so forth. And I saw a lot of limitations with the decompression tables and all that stuff. And at the time, I was a physics and math and pre-med major. And so that inspired me to really get into the physiology and the physics, the biophysics of diving. And then it's kind of a long story, but when I graduated, I wasn't ready to commit to grad school or med school because I wanted to do all these things that weren't just down one path.
Right.
And so I went out and worked as a commercial diver. And I loved it. In fact, I was on a great job down in Peru where we were rebuilding these platforms that had completely corroded over the previous 20 years because they had no anodes on them. And they sent me down as the engineer and a diver, and so I had to figure out how to repair them. And we came up with all these clever techniques, and it was a very challenging job working with the cast of characters that ranged from special forces assassins from Vietnam to welders and so forth. But I really enjoyed the reality of that. I mean, it was, unlike the sort of the more sheltered college environment where, who you know and what your family did. And here it was like, what can you do in the water on the end of the hose?
And that's what mattered.
And that's what mattered. And so that really inspired me. And then it turned out I stayed with that for a while, and I really wanted to do more graduate level work with decompression and so forth. And the medical director of the company I worked for at the time, which is named Ocean Systems, was a famous guy named Dr. C.J. Lambertson, who invented the rebreather and is the founder of the SEAL teams, and a truly remarkable guy.
Absolutely.
And he took me under his wing, and I did an independent study and decided to go to grad school, not med school. And so I started a graduate program at University of Pennsylvania under Lambertson, and that turned into a 30-year relationship where not only did I get my Ph.D., I developed new models of how bubbles grow and influence decompression, and then Lambertson and I would generate new decompression tables. But I was doing this all while working as a diving supervisor out in the field. And so we would generate the new tables, and then I would go out and use them. And I had special dispensation to run these jobs from our safety director, who was tied in with me and Lambertson. And so
they allowed you to actually kind of test out what you and Lambertson were developing in the laboratory. They allowed you to test it in the field?
Exactly.
That's impressive.
Yeah. In fact, Lambertson would say that was his ultimate goal was to make the field the laboratory. And by me taking these tables that we developed and taking them out in the field and doing Doppler measurements and feeding back to them, in this short period of about 3 years, we generated tables that became the oceaneering standard that literally, there's probably been 10 million dives done on those now. And before we did that, the Navy Cert O2 tables really were not good tables. In fact, I was on a salvage job where we were diving right at the limits of those tables, and we had about 20% DCS. I mean, these were like, Z dives and so forth. And so we completely transformed that with the bubble model, generated tables, and dropped the DCS incidence to like 1 in 10,000.
Wow.
And so that was a really powerful time. And
Yeah.
It was a real honor and pleasure to be able to work with Dr. Lambertson. And then our safety director was a guy named R.G. Miller, ex-Navy officer and so forth. And so really powerful times.
That's incredible. And Dr. Lambertson is, considered to be kind of one of the godfathers in our field of diving medicine. What was it like working with Dr. Lambertson?
It was great. He was an amazing guy, and I tell the story that I first started reading his books when I was an undergrad, and always was like, God, I'd love to meet this guy. And then there you meet him. He's interesting guy. Terribly interesting. He actually looks professorial, had a beard, was older, although at the time he was probably about my age now, but he seemed quite old. And it turns out, like when you shake his hand, it's like, man, he could squeeze your hand off. And So he actually was very much of an operator during World War II, and I kind of knew that, but it was all classified. And only late in his life, I used to fly a T-38 up to Penn just to visit with him on some of the NASA work we were doing, and some of his stuff got unclassified. But he did like the first lockout from a moving submarine, and wrote many, many papers on tactics and strategies for undersea warfare and so forth that really influenced everything, on top of all the physiological work that he did. So, I mean, he was just a personal friend and kind of a father figure. I could talk to him about anything, be honest with him, and he would, when I was there, he would just make the time to sit and talk, and he was also a great mentor. And like writing my Ph.D. dissertation, he's hard on me. I mean, he made me do that right. And he read every word. And
a good mentor will do that.
Yeah, so he was very engaged. And then we had ongoing relationships. When I was vice president of Oceaneering, we continued to develop new things. And we had a big project with the British Department of Energy to do some new tables for the North Sea. And so we had this ongoing relationship. And then fast forward, after I was an astronaut, I became the principal investigator of all of our pre-breathe procedures for doing spacewalks from the space station. And I'll talk about that maybe more later, but Lambertson had been an advisor to NASA for decades. He was actually the chief life scientist for the Mercury program, and he was on all the review committees. And so he was reviewing my work, and the people at headquarters said, that's a conflict of interest because he was your mentor and stuff. And
He's far
was
from
like,
it.
Baloney. And I said, man, I'll tell you, there's no one's going to be harder on me than Dr. Lambertson.
Yeah.
So we kind of fought off the bureaucrats on that and produced stuff that has really enabled the assembly and maintenance of the space station.
Yeah, that's really impressive. I didn't realize that Dr. Lambertson was so involved with NASA, so that's new to me.
Yeah, no. In fact, even well before I was an astronaut, when I was working with him, when I was at Oceaneering, he had a advisory role to come up with the diving techniques for the MBL, and I was on that committee, and we developed all the nitrox procedures and stuff that later were used in the MBL.
The neutral buoyancy lab at NASA they use it to train astronauts for spacewalks.
Exactly.
Yeah, very impressive.
A lot of connections between sea and space there.
Yeah, absolutely. And speaking of, so you started to transition into working with NASA through Oceaneering, through the development of Oceaneering, correct?
So Oceaneering, I became vice president of Oceaneering, the international corporation that did subsea work. And I was vice president of special projects. And then I convinced the board in 1987 to let me start a company called Oceaneering Space Systems, which was to transfer all the subsea robotic experience, life support, physiology, and so forth to NASA. And so I started the subsidiary company, Oceaneering Space Systems, in 1987. And we did a whole bunch of robotic stuff. We invented this cryo pack where we actually used liquid oxygen for breathing and for cooling, and that's a long story. But and it was an elegant solution, and there were issues about using that in microgravity because there's no gravity feed to attract the liquid oxygen.
Right. And
so we came up with this clever idea that we called the magnetic intake doer, and it turns out that oxygen is paramagnetic. And so you could use a magnet to attract the liquid oxygen into the heat exchanger between the liquid cooling water that circulated around the astronaut. And it turns out that the harder you work, the more heat you generate, the more gas you would vaporize, and you're exploiting your body's own biocontrol processes to regulate these things. And so we had the idea, and as a lean, smaller company, we decided to go test this, and if it would have been a large aerospace company, they would have got a study contract for a couple of years and so forth, so forth. So, we went out to Air Products and got some liquid oxygen, and we got a styrofoam cup, and we got a magnet, and we put on our goggles, and we dipped the magnet in the oxygen, the liquid oxygen, and pulled it out, and there's a big glob of oxygen all around it.
That's really cool.
And so that was the start of the magnetic intake doer. And then we built this, we did a lot of physics with this, where we actually had the magnet and we would flow the oxygen around it. and it created a magnetostatic pressure field that would repel the gas phase. So if you injected bubbles, it was repelled by this magnetostatic pressure field. And then we actually won a large contract, multi-million-dollar contract to build what was called the subcritical oxygen, liquid oxygen storage system. And, we beat out the major aerospace contractors for that. That was exciting for our young company at the time. But so, that transitioned us into the space world. And then we did a lot of stuff with robotics because, at the time, there were two camps in NASA. There was the Goddard roboticists that thought you could do everything with a robot. And I remember a meeting that we had with Gene Kranz. This is like 1988. And he's like, they're talking about the Golden Monkey, which was the flight telerobotic service. And so there was this huge polarity about what you could do with robots. And in the subsea world, we do things on a time scale much faster than NASA would. And I actually have a presentation I give that's called the Darwinian evolution of subsea work systems. But we built all kinds of different robots, different combinations of humans and pressurized bells with robotic arms and, atmospheric diving suits and so forth. And so we really learned a lot about how you work with humans and robots and how you have to design the task to be done by the robot and which task makes sense to be done by the robot. So all that experience we packaged up into a very systematic methodology that we then applied to NASA to figure out which parts of stations should be designed to be serviceable with robots but also compatible with astronauts. And things like some of the subsea tooling that I worked on was this conical interface that we actually had on every valve on a subsea production facility that turned the task into a very simple task of just docking the ROV with that interface. And then there would be different tools within the work package on the ROV that would turn the valve and so forth. And that really transformed the subsea ROV intervention stuff. But that mapped right into what's called the microconical interface, which I designed and that Tom is probably familiar with. But they're all over the space station. So there's really a lot of synergy between working underwater and working in space and the design of the tasks for human and robotic compatibility.
Instead of reinventing the wheel, just taking what's been learned already, like you said.
And the other thing that was interesting is that when we first started Ocean and Space Systems, a lot of the aerospace contractors would come out to our shop and we had these atmospheric diving suits that weigh about a ton and so forth, and they made sense, and they worked underwater for what we were doing. And, I was selling the concepts, the operational knowledge, design knowledge that we would apply to NASA. And some of these folks were, they thought that they were going to buy a suit from us or something. So they'd come out and they'd see this big suit and say, we can't use that in space. And I was like, look, we're not selling hardware. We're selling the experience and the engineering base. And so that actually kind of propelled us into the whole space business. And the company that I started with just me and a secretary, and then I went out and I hired every commercial diver that I knew that had gone back and got an engineering degree, and then I combined that with going up to the best universities and personally interviewing the top talent, and we put together this magical combination of seasoned commercial divers and smart as heck MIT and JPL grads, and really did an amazing amount of work. And then at some point in this process, I applied to be an astronaut and got selected. And that was a hard thing to leave that team. But
I was going to ask, what would you possibly give up that exciting field for just to become a worker bee as an astronaut? Because at the astronaut office, they don't actually sell that job on the basis of, hey, you'll get to be creative here. Mm-hmm. And usually it's more you're going to be a proxy for someone else's work and genius and insight and inspiration, and then you're going to be applying that in space. So it's an interesting question. You sound somewhat like Bruce Willis in Armageddon, the oil roughneck coming out of that industry and going to work as an astronaut. And I think that's an interesting background that you've got, that you brought that over to the actual crew member job.
Yeah.
Did it measure up to what your hopes were?
Yeah. So, I back in my early teens, I was, into subsea work and Jacques Cousteau, and we were doing Tektite and And at the same time, we were doing Skylab. And so I kind of put together that living and working in space and living and working underwater were very similar. And I was, really into athletics in school, and I wanted to do the most I could with the life I have, both mentally and physical. So I set the distant goal to be an astronaut, and I wanted to do it through my path, which was subsea, even though people say, well, you ought to join the Air Force or whatever. So I kind of did my thing. And then I got into the office, and as Tom says, the first year you're an ass-can, and you've got, you show up at your astronaut office desk, and there's a pile of manuals that go up from the floor past your desk, and it's like you've got to learn all this, and you're like, wow, and then you got to learn to fly a T-38 jet, and then you just start working hard and taking it one day at a time, and it all starts to come together, and then next thing you know, you're flying in space, and I'm probably somewhat different, maybe a lot different than most astronauts. My area of academic expertise was directly relevant to EVA. It wasn't like I was a material scientist or something else. And so everything that I wanted to do creatively and academically was directly relevant to our job. So in addition to having the conventional astronaut office jobs, working in the Shuttle Aviation Integration Lab and as a C-squared and as a Capcom, I had a whole nother life going on all the time where I was designing tools, and then doing all these pre-breathe procedures. One of the tools that I designed that doesn't get much press, but it probably enabled the building of a space station, is this thing called the body restraint tether. And I had actually prototyped that at Oceaneering because working underwater on a platform, we would typically tie ourselves off from our waist if we're doing precision welding or burning work, and you had more control. And I started looking at the at EVAs, and we carry these foot restraints around that are a bit of a pain to translate with, and then you stick them into a what's called a worksite interface, a WIF, and then you get in the foot restraint, but you can only reach a certain amount of distance, and then you got to go through the whole thing again. And to me, that was just crazy overhead. And so I invented this thing called the body restraint tether that came off your suit, and it was a clever kinematic design based on my robotics experience, but it had a 3 degree of freedom friction joint that could do 360, and then that was combined with this flexible ball stack, and on the end of it was a clamp that could attach to a handhold. And the handholds were all over the space station. So anywhere an astronaut was going to go, there would be a handhold. And then with this body restraint tether, once you torqued on a collar, it would tighten up that ball stack, and now it provided some degree of restraint. In between the 3-point base of stability you would get from the body restraint tether, another hand on a handhold, and a third hand with a power tool or doing a connector, it turns out that probably 80+% of the tasks we needed to do on station, you could do with this body restraint tether. And you could pull up and clamp in a matter of 10 seconds or something with the body restraint tether instead of having the overhead of carrying a big PFR. And so
a PFR being?
I'm sorry, portable foot restraint.
Okay.
And so, I built it, and I think, Tom, actually, you probably used it a lot on your flight, right?
It was a dream. It enabled you to scramble anywhere on the space station and then just grab onto a handrail with your third arm, which you provided, and then that left your hands free, and you could turn your body left, right, in and out. And then you could carry it around just by bending it over your shoulder, and it was out of the way of all of your other tools. So it was a very handy device that's used today on the space station.
And interestingly, I always knew that we could use it to also translate like PFRs and ORUs and stuff, but at first I didn't want to oversell it. And now we're actually carrying these things called the Broom, which is this 500-pound ORU that we use in the rotary alpha joints of the solar array. So it became much more versatile than the initial focused application.
Well, essentially, you talked about the Darwinian evolution of subsea systems, and now this is the Darwinian evolution being applied and even continued with respect to space operations. So it's really impressive that you've taken that information and translated it over. So can you tell us a little bit? So, my background as a diver, I know what it feels like to go diving and to be free-floating underwater. And how similar is extravehicular activity or EVA experience to diving?
So what's similar about it is you're working in a three-dimensional hostile environment, so you can't breathe the air, or there is no air either in sea or space. And the way you think about doing that operation and planning it and designing the task are very similar. And you have to go in with a good plan A, plan B, plan C, know exactly what you're going to do and so forth. In terms of the actual mechanics of it, it's very different. Underwater, we're not in pressurized suits, so we're wearing either a wetsuit or a hot water suit, so you have far more mobility and dexterity. In underwater, a lot of times you're working in water on the bottom when the mud is stirred up and you literally have no visibility. So you're kind of doing things by imagining them in your head and using your hands to feel and talking to topsiders, looking at the blueprints and talking you through where you go and so forth. And that's an art form and challenging. And you tend to use all your body senses, the proprioception, you feel around with your legs where the next thing is. And it really, you develop this acute sensory awareness of your environment and how to work in it. And those are all great skills that translate to EVA. In EVA, you're in a pressurized suit that's pressurized to 4.3 pounds per square inch, which is the same as the inflation pressure of a football or a basketball. So every time you move, you're fighting that inflation pressure. Every time you close your hands, you're fighting against that. And that's a whole different level that requires additional training and so forth. And then the other thing in space is that even though you're weightless, in quotes, you actually are not massless. And you in the suit weigh over 500 pounds. And if you get that suit going fast in space, you are going to tumble out of control. And so my motto was always, you cannot go too slow. And never let your hands get moving faster than your brain. So in EVA, it's very much a mental game. You're thinking about what you're doing now, where your buddy is, where the airlock is, where your tether is, what the next task is, where I am in the timeline. And all of that mental stuff I got from diving in spades, because a lot of the diving I did was surface diving, where you had very limited bottom time. Like at 300 feet, we'd have 30 minutes on mixed gas to get a whole bunch of stuff done. So you had to be acutely aware of that. And so those skills translated right into the EVA part. But so it's very much a mental game. And so the mental aspects and the planning aspects and the task designs are the same. The physical sensations are different. And then in space, unlike working deep in the ocean with muddy bottoms, you have unlimited visibility. You can see literally millions of miles. And even at night, we can turn on our helmet lights. And so that was much easier because you had this great visibility.
StemTalk is an educational service of the Florida Institute for Human and Machine Cognition, a not-for-profit research lab pioneering groundbreaking technologies aimed at leveraging and extending human cognition, perception, locomotion, and resilience.
I'd like to ask you, Mike, about one of your shuttle missions where you were going to be one of the EVA crew members. It was rare to get a space shuttle spacewalk in the mid-'90s. We hadn't gotten into the space station construction yet. And yet, a few weeks before launch, you sustained an injury, and it might have threatened your ability to go out on a spacewalk. Why don't you tell us briefly about that story?
Yeah, Tom, I'm glad you remembered that. Tried to forget it. But no, so we were actually and as Tom points out, I was the first one in my class assigned to do an EVA. It was a very important EVA because we were going to evaluate all of the assembly and maintenance techniques that we would use to build the space station. And we were going into quarantine on a Friday night, and we got word that
a week before launch,
we got word that there was some issue with the solid rocket booster O-ring and that we were delaying. And so I went out and got a date and went to Galveston to see a play at the Grand Theater. And as it does occasionally in Houston, there was this torrential downpour. I mean, unbelievable downpour. And I dropped my date off at the front of the theater and I went around to park in the back. And then I got out of the car and I had this sort of broken little umbrella, and it was dusk, or actually it was evening. And so I was running through the parking lot, and there was a median strip with newly planted trees with guide wires. And so I tripped on this guide wire holding my umbrella, and I fell down and I dislocated my shoulder. And I remember very vividly thinking, okay, this is going to be interesting. And I tried to put it back in. I was like, maybe nobody saw this. I could put it back in, but it wouldn't go back in. And it was actually a pretty severe dislocation. So I went into the theater and called the ambulance. And I remember thinking I could have two attitudes. I could say, God, why me? I've worked my whole life to be an astronaut. I get assigned to an EVA, and now this happens. Or I could take a good attitude, which is, hey, if I can do this, I will. And if not, it's not about me. It's about the mission. And so I had a absolutely great attitude. I had the ER guys down in Galveston call our flight docs, and they were right in the loop on that, and came to see me the next day and lined up the best physical therapy on Monday, and my crewmates were great, and so I started rehabbing. And then on Tuesday, we actually had a sim because we had to stay current because we were delayed day to day. And on my first flight, I was EVA and also arm operator and a whole bunch of other stuff. And so even in a sling, I was able to operate the arm and grab a satellite and so forth. And at first, nobody thought I was even going to fly. And then by Wednesday of that week, they said, well, he can fly, but probably not do an EVA. And they had Jan Davis was assigned to be my backup. And so she was following us around these sims. And I was rehabbing, 4 hours plus a day. We actually launched, I think, 8 days later after this dislocation. And our plan within the astronaut office and our crew was for me to rehab in space because the spacewalk wasn't until like day 12. And so that would give me, almost 20 days before I had to go. And the day before the spacewalk, I was going to see if I could get in the suit. And if I could, then I was going. If I couldn't, we'd have Jim Newman do it. And everyone kind of bought off on that except the medical ops group, and I won't mention names, but the head of that wanted me to prove that I could get in the suit before he would sign the flight readiness review. And so it was set up at day 7 before we flew to the Cape for me to do a demo that I could get in the suit. And it was over in what's called the Blue Room in Building 7. And my commander was a guy named Dave Walker, who I love dearly. He's no longer with us, but coolest guy, best team builder. Can tell you stories forever about him and what a tight crew we had. But he set it up with the suit techs to take the arms off the suits, and he got me over there 15 minutes early. And I was over there, and we had my outside orthopedic surgeon was there, and everybody was there. And Tom knows this, but it's really hard to get into this suit. You almost dislocate your shoulder to get into the suit, but if you take the arms off, it's trivial. So the arms were off the suit, and I got in the suit.
You got in the suit?
I got in the suit, got out of the suit. They put the arms on, and then 5 minutes later, the head of Med Ops comes in his coat and tie, and they all said, Mike got in the suit. And he was like, okay.
Sign off.
And then the outside orthopedic surgeon said, and once he's in there, there's no way he's going to dislocate his shoulder.
Right.
Because there's not
Too
enough
constrained.
room to. Right. So we went to flight with that. I did the spacewalk. It went great. I was about in as much pain as a human can stand. It was a huge mental focus, but it all worked out.
That's a great story.
Right, and then you got to go to the space station to install, I think, the airlock. Was that your mission?
Yeah.
And then you got to do some EVAs in connection with that. So in the end, you got to use that on this facility, this outpost that you'd been planning for years. Must have been very rewarding to do that.
It was. And in fact, on top of that, another big development team that I led was developing the pre-breathe protocols to do spacewalks from the space station. And on Space Shuttle, we would actually depressurize the cabin to 10.2 psi, 26.5% oxygen, and stay there for at least 36 hours, only requiring 40 minutes of oxygen pre-breathe in the suit to go out the door. The space station was so huge, there was no way that you could depressurize the whole station to 10.2 and so forth. And so our baseline going in to space station was to camp out overnight in the airlock for about 8.5 hours. And for a number of reasons, including crew isolation, the fact that to depressurize the airlock to 8.2, 26.5% used oxygen, and then there were no bathroom or food or anything in the airlock. And so in the morning, you would have to put on an oxygen mask, repressurize the airlock to 14.7 psi, and then skirt out into the station on a 120-foot-long pre-breathe hose and use the head and grab some chow and then get back into the airlock. And so nobody liked that. And so I started this program called the pre-breathe reduction program, where our goal was to take our pre-breathe times, which were 4-hour resting pre-breathe times, or the 10-2 stage decompression, and cut that in half to a 2-hour pre-breathe with similar or lower risk than we had on shuttle. And I could spend a day talking about everything that went into that, but we had a great team and we hit the ground running. And there were 2 sets of enabling research that had been done that suggested that we might be able to be successful on this. And one was work that Dr. Andy Pilmanis and Dr. James Webb did at the Air Force, where they did 10 minutes of exercise, fairly vigorous exercise, 75% VO2 peak, during oxygen pre-breath. And the theory was that exercise would increase your cardiac output and blood flow, and then therefore carry more nitrogen back and basically shift your nitrogen elimination half times from 360 minutes to something much faster, so you dump a bunch of gas. And
you're breathing pure oxygen the whole time.
You're breathing pure oxygen the whole time, and I'm not sure who our audience is, how technically, physiologically savvy they are, but oxygen, of course, chemically reacts in the body, so any inert gas like nitrogen that you have in your tissues diffuses from your tissues into your blood under the maximum diffusion gradient or electrochemical potential gradient. So you're just dumping the nitrogen as fast as is possible. And the Air Force did that with a 10-minute pre-breathe protocol in a 1-hour total pre-breathe, and they still had just under 50% DCS, which wasn't going to cut it for us.
The bends for their pilots.
Yes. Mm-hmm. And then the other set of experiments were done by Dick Van and a guy named Dr. Michael Powell, who had this theory that if you didn't ambulate, you wouldn't create these lower body musculoskeletal stresses that would cause nuclei to form. Sort of, you wouldn't shake the Coke bottle in very simple terms.
Essentially the seeds so that the bubbles form from.
Right. And we can get real technical on that or not, but you actually have to have these nuclei or you couldn't explain why you would ever get the bends. And so the idea was that we don't actually walk while we're in space. And so we designed a whole new protocol where we did this exercise pre-breathe, and we designed the EVA simulation to be more realistic of space station EVAs. And we do ingress foot restraints. So we actually developed this pulling scale system based on the body mass index. And we actually designed the whole EVA simulator to match the metabolic profiles that we had seen in EVAs and so forth. And we built this test bed. And then I started this multi-center study with a lot of the top people from undersea physiology that I had known. And so we worked with a guy named Ron Nishi up at the Canadian Defense and Civil Institute for Biomedicine, worked at Duke as a test site with Dr. Dick Van, who's been there forever, and then at the time a new guy named Dr. Neil Pollack, and also Wayne Girth was part of that, who's now at the Navy. And then at UT Herman with Carolyn Fife and Bruce Butler. So we really had the top talent in underwater physiology involved in this testing program. And long story short, we ended up producing this amazing exercise pre-breathe protocol, and we had no bends and very few bubbles in 50 subjects that actually met this accept reject criteria that we spent a year developing to make sure that it would be acceptable and safe.
Right.
And so that was a lot of work. And then I got to actually use the protocol that I had designed and led on the first spacewalk from the space station.
Oh, cool.
So that was another chance to use something that I had been part of the development of.
You can see Mike doing that pre-breathe protocol in an IMAX movie called Space Station 3D.
And stepping through all the bits of it.
He's wearing an oxygen mask and he's on an exercise bike and he's, moving his arms around, and so he's executing the protocol that he planned, and he didn't get the bends.
So I was actually, for our audience, I was actually a research assistant on Mike's pre-breathe protocol
right.
at Duke University
I
with Dr.
remember that.
Van. And Dr. Van was a Ph.D. advisor, but I got to sit in the chamber and do Doppler monitoring of the subjects and look at how much they were bubbling at altitude with their throughout the protocol.
Yeah, that's great. Yeah, the chamber techs, that job you did is a very important job, and
yes.
It requires a lot of skill because we had very tight timelines, and if you would blow a timeline on just the Doppler measurement, that would be reject criteria. So it's a very, very challenging job, and and the folks at Duke and all the other centers did an amazing job on that research protocol. So, but we actually used this, and it really, we probably couldn't have built this station as effectively as we did if we didn't have this protocol, because all of the assembly flights required use of the space station RMS for specific tasks, and so the crew coming up was the most trained on those activities, and then we also had logistics and stuff to transfer from the shuttle to the space station. And if we didn't have this exercise pre-breathe protocol, we would have to have the hatches closed during the EVAs. And there was a flight rule we had that if you had the hatches closed, you had to be in the vehicle that was your vehicle. So if you were a shuttle crew member that was trained on the station RMS, you had to be in the shuttle and couldn't do that. And so the exercise pre-breathe protocol actually facilitated the early assembly of station. And then over the years, we've done more and more research, and now we have what's called the in-suit light exercise protocol that saves a bunch of complexity of the other exercise protocol, and we use that now routinely on space station, and we've never had any bends. So we're up to, I don't know, pushing 200 EVAs with these procedures that we developed with no decompression sickness.
Very impressive. So, Mike, you have been leading this pre-breathe reduction program. You've been involved in a large number of other development projects and biomedical research projects through NASA. What other current projects are you working on?
So, a lot of stuff going on now. I'm leading what's called the Human Integration Team, Moons of Mars team. So we're actually developing the details of a Phobos mission, which is a moon of Mars, where we would actually go there in the 2030s, and that mission would actually serve as a framework to develop about 90% of the stuff we would need to do a Mars surface mission. So it's the transportation system to get there. We actually would go up with the crew to high Mars orbit, but we would have pre-deployed a habitat and this thing called the pressurized excursion vehicle that I'll talk about more later. Those would be pre-deployed to Phobos. And then the crew would actually taxi from high Mars orbit over to Phobos in a Mars ascent vehicle-derived taxi. So it would be a way to test the Mars ascent vehicle. And then we get to Phobos, and long story, we would end up rendezvous and docking with the HAB, and then we would do these excursions in the pressurized excursion vehicle, which is another thing that I'm sort of the father inventor of, but it's a whole new class of exploration vehicle where instead of fighting your way out of a 14.7 PSI station with all the pre-breathe, we actually have this small cabin that has great windows, and 2 people live in it for 2 weeks or more at a time. And the pressure of that cabin is 8.2 pounds per square inch with 34% oxygen. So it puts us in a much better posture for not having to denitrogenate to avoid decompression sickness. And then we actually have the suits, instead of having an airlock, and as Tom points out, on my last station flight, we installed the airlock and made the first spacewalk from the airlock. And Tom can attest to this, but airlock ops are not fun. I mean, it's a small thing. You got 2 guys in there. You're got other ORUs, and you sort of have to open this hatch that doesn't really.
It's 2 hippos in the front seat of a Volkswagen.
Yeah, that's a good way to put it. But and there's a lot of overhead with that because you don't want to dump all the gas that's in the airlock because it weighs a lot, and so we have to reclaim that with this vacuum pump, and that can take 30 or more minutes, and all of this is just overhead that it takes to get outside of the vehicle. And I have an index that I invented in diving I call the work efficiency index, but it's basically the work time you get outside divided by the overhead it took to get outside. And on station, we spend about 2.5 hours inside for every hour outside. And to me, that was crazy because in diving we get way better than that. We're 6, 8 type of thing. And so we implemented this thing called a suit port on the back of the rover, so the suits are actually outside of the rover cabin, but they're attached, and they have a flange called a suit port interface plate. They're attached to the cabin with this suit port that basically is a Marmon clamp with an inflatable seal. So the suits are sealed to the cabin, and there's a bulkhead hatch inside, and you open that hatch, and then you open the backpack of the suit, and then you step into the suit, And we have electromechanical actuators on the bulkhead hatch, which closes the backpack of the suit, and then you lock it with an over-center cam on the front of the suit. And now I only have to depressurize this small vestibule between those two hatches, and that's about a quarter of a cubic foot versus a 250 cubic foot airlock.
So this is similar to the suit ports that you implemented in the new lunar rover design.
Yes. In fact, this whole design evolves directly from that. And the whole concept is we have this cabin that is optimized for viewing and low overhead EVAs. And then we can combine that with different mobility elements from a chassis for Mars surface or lunar surface work, or in the case of Phobos, where there's really not enough gravity to drive, we have a reaction-controlled jet sled, and then these hopper legs where we can hop around and so forth. And we're also looking at using that same cabin as the cabin for the Phobos taxi and as the cabin for the Mars ascent vehicle with a slightly different configuration that wouldn't weigh as much.
And Phobos, Mike, tell us about the advantages that gives us for Mars exploration. And, it's a very low-gravity body. It's about the size of a big city, perhaps. What advantages do we gain from being around Phobos?
Yeah, that's a great question, Tom. And first of all, Phobos is very interesting.
Or Deimos, for that matter.
Yeah, or Deimos, and we're looking at both. But Phobos is very interesting scientifically. It'll tell us something about the natural history of the evolution of Mars. There's these fissures on Phobos that we have different theories of why they're there, but they seem to be quite deep and long. There's a lot of craters on it. There's these monoliths that are like 120 feet tall by 40 feet wide that look rectangular like 2001, and we have no idea where they came from. So there's all kinds of scientific interest. There's almost certainly Mars surface ejecta from meteorite collisions with Mars, and it's probably also an accretion point from other materials from the asteroid belt. So it's scientifically interesting in itself.
Pick up pieces of Mars on the moon of Mars.
On the moon of Mars. And the other thing is that it is so much easier to go to the moon of Mars than Mars surface, because Mars is the worst place in the solar system to try to land because there's just enough atmosphere to get you hot, but not enough to slow you down. And so it's very difficult to land things on Mars. And we will do that someday, but we don't have the technology to do that with the kinds of payloads we need right now. And so by going to Phobos, we basically develop all of the infrastructure we need to go to Mars surface, the transportation infrastructure, the cargo pre-deployments that we're going to need, this cabin that will be used as the Mars surface rover. All of that is bought down. And then on top of that, from Phobos, we have the capability to do what's called low latency teleoperations of Mars rovers. And right now, when we operate from Earth, these things go tiny distances, 50 feet a day or something. So it's very slow and methodical. If we're on Phobos with the crew, we can operate these things with about 250 millisecond time delay, which is really nothing. And so we're able to go much faster and farther and probably go places that you wouldn't want to go if you didn't have this capability. So it's sort of enabling, certainly in landing site validation and possibly in offloading payloads and developing the infrastructure and stuff. So there's that advantage.
Stepping stone, sort of.
It's absolutely a stepping stone. And as I've led this study, I've been, probably overstate the word, but sort of militant about not developing Phobos unique things that would stick us there for years. So Phobos is a stepping stone, and 99% of everything we would use to go to Phobos takes us toward Mars surface. And it's certainly more affordable, and I think it serves as a very effective stepping stone to Mars surface. And on top of that, Mars is only 9,000 kilometers away from Phobos, so every exploration activity or public outreach event that we do will have Mars looming large over the horizon and keep our focus on where we're going. And so I think it's got multiple advantages, and we can go there in the 2030s. And my hope is that we actually sign up to that and have a plan that we can close a budget around and really start having a focused exploration effort that starts with doing the right but limited things to cislunar space, then moving on to Phobos, and then eventually to Mars surface.
So, Mike, you've led an incredibly inspiring and interesting career pathway as you've made your way into the research that you're doing and also becoming an astronaut and what you've accomplished as an astronaut. What advice would you give to someone who's an aspiring astronaut?
So that's a great question, and the first thing I always tell these kids is, first of all, get as much education as you can, and then do things that you like, because if you like them, you're going to have a good life. You enjoy them. You're going to be good at them, and do things that you like that sort of vector you toward being an astronaut. But don't do things that you don't like that you think will make you a better candidate to be an astronaut. So if you do things that you like, you're going to be good at it, and that increases your chances of being selected as an astronaut. And then throughout your career, learn to be a team player, because astronauts all about team player. It's not about individual superstars. You got to play as a team. You got to understand what your capabilities and limitations are in other people, and learn to get the best out of the team. That's super important, and just go for it.
Perfect. I think that's great advice. So with that, I'm just going to thank you, Mike, for joining us today.
Okay, well, thank you. Good questions. Good discussion.
Great to talk to you, Mike, and great to work with you over all those years in space.
Yeah, Tom and I go way back, and he's always a great guy to work with and talk to in the hall. And I think we worked together on a lot of the station assembly stuff. And you look back finally on those years, and it was an exciting time and all this stuff.
And you're still wrapped up in making the future happen out there with human exploration. And I think the listeners and I have learned a lot about your background that I didn't know before.
Well, and I have as well. And I'm honored to have joined both of you actually today. That was great.
Okay, well, thanks so much, and you all have a good day.
StemTalk. StemTalk. StemTalk.
So that was a fascinating interview with Dr. Gernhardt. I actually had no idea how much impact his work has had on the space exploration community. And what I found particularly interesting was the emphasis on how much overlap there is between the undersea world and the space world, and how much his work has transitioned from undersea operations to space operations.
It's a smooth transition, and he depicted it beautifully. Mike is a great guy and a valued collaborator. In fact, a man for all seasons.
I can't agree more. I invite you to visit the StemTalk webpage, where one can find the show notes for this episode and all the others, stemtalk.us. This is Dawn Carnegie signing off for now.
And Ken Ford saying goodbye until we meet again on StemTalk.
Thank you for listening to StemTalk. We want this podcast to be discovered by others. So please take a minute to go to iTunes to rate the podcast and perhaps even write a review. More information about this and other episodes can be found at our website, stemtalk.us. There, you can also find more information about the guests we interview.